Hello, welcome to another episode of Computer Music Practice Examples. In this one, we are going to learn how to create a APG, an audio palindrome generator. It's an app that when you put 3 audio samples like this one, bell pepper, chicken, and bass clarinet, it's going to automatically create a sound file that sounds the same when you play forward and backward, right? So even you reverse the sound, it's going to make a same sound. So let's hear it, and let's hear what we are going to make, and then we are going to explain what's going to be happening. So here's the bell pepper. Here's the chicken. And then bass clarinet. Okay, so the regular palindrome will have no repeats, and when you put all these 3, you're gonna hear a bell pepper, chicken, and bass clarinet played at the same time, but reversed in the second half. Here it is. Now, what we are going for is go one step further. Now, what we are going to make is make a palindrome, the same principle, but we can control how many times each sample will be repeated, and also we can change the pitch and the speed of those each sample, so it's gonna sound something like this. Okay, good. So that's our goal, to learn how to do it. Just like the other CMPE episodes, we are going to rely on block diagrams and step-by-step procedure of creating a sample, creating a synthesizer, creating a loop, and a function that plays the loop and the synthesizer, and finalize that with the graphical user interface. So if you are not familiar with the block diagram labels and how I usually proceed, please check out the introduction Google slide and a YouTube video. And also, before we go further, make sure that you check out the app and the demo. And if you are a SuperCollider user, it will be really helpful if you download and open the attached the linked SuperCollider files. Okay, good. So let's get going. So first thing we are going to do is we are going to make a little plan, right? We are going to create a GUI, and we are going to use some randomized functions, random generators, but also we're going to have a very specific way of playing and timing certain audio files. Okay, so here you may notice that I changed a little bit of order. Usually I create a synthesizer, loop, and a function, but for this one we are going to create a synthesizer and then create a little function to calculate the timing of the playback and repeat that procedure using a loop. I think it's gonna be easier if I use the little pointer for this presentation. Okay, so we listen to this, and there's a little demo video of that too. But let's go over the plan again. Make a sample playback instrument, and make a function that calculates the timing of the palindromic sample playback, and make a routine that repeats the palindromic sample playback. And as a user, we can control the number of repeats and the range of the pitch randomness. And we control that with the GUI. Okay, so very first thing we are going to do, as always, is to make a synthesizer that makes a sound. And despite the complex look, our synthesizer only has 3 parts. One is the audio player, sample player. The other one is the mono stereo detector. And then a little amplitude envelope. Now, mono stereo detector, we explained this in a SIOE, but it basically prevents an error when we input a mono file instead of stereo file, and then it will basically convert any mono file into the 2-channel stereo file. Now, my amplitude envelope will be a kind of more preventive measure. What it's going to do is it's going to make an amplitude envelope with an amplitude of 0 at the beginning and the ending of sound. Basically, we're gonna prevent little clipping sound when the beginning or the ending of audio file is at a non-zero crossing point. So it's a more of a preventive envelope. You're not gonna hear the effect of the envelope if we do it correctly, and the duration of that will be calculated by the number that we put for the rate and the reverse and multiply that with the overall amplitude. So let's take a look at what's going on at the audio file player here. At the end, play buff will play the buffer which contains the audio file. So we are going to play an audio file. Okay, and when we put the sound into the buffer, we can get all sorts of information such as the number of channels, okay, and a sampling rate, and the number of frames. Number of frame is the total duration of the audio file in samples, and if we divide total duration of the total sample divided by sampling rate, right, we get the duration of the file in seconds. Now we divide that with the rate, how fast the audio file is being played. We can automatically calculate the duration of the amplitude envelope. If my rate goes up, my duration will get shorter while the pitch is going up. So if we do the duration divided by rate, then my amplitude duration will shrink or expand according to the speed of the sample playback, which will change the pitch. Now, I'm gonna have one more multiplication here, reverse, which I will input either 1 or -1. If my rate is at minus number, supercollider will play buff will interpret that as the reverse playback. So if my rate is 1, it's going to play the sound in a regular direction. But if my rate is -1, then it's going to play the sound in a reverse direction. It's going to reverse the sound. It's a very convenient mechanism for our algorithm. Okay, so sample playback with the simple clip preventive envelope and a little error preventive stereo mono detector. So it's quite a simple synthesizer. What's challenging is calculating the timing of the playback. Okay, so let's kind of think about how we can calculate the timing of those first sound and its opposite reverse sound. But before we do that, I think we should go a little bit on the supercollider code. Okay, so here's our supercollider code. Step 1. Notice that there are 3 synth depths, but they are basically copy and paste the version of the same thing, but with a different buffer number. So each I play samp will play a different sound file here. So here we are going to play chicken and a little drum machine and a beatbox sound. Okay. And now if we make a synth I play samp 0, with the reverse sound -1, this sound, this sound, the chicken, which is assigned to the buffer 0. We're playing reverse. Let's run this one. Okay. And if I change my rate, then it's going to play twice as fast at a reversed direction. Okay, so that's our basic instrument. Now we calculate the timing. Now, so the goal is, right, you have to have a palindromic position, meaning that from the midpoint of the total duration of this palindrome, the ending of the first sound and then the beginning of its reverse sound should be equidistant from the center in terms of the timeline. Okay, so I guess there's many ways to calculate that, but here's how I did it. First, I defined the total duration as the longest file duration times 2. So SuperCrowder will detect the duration of the longest file, and I'm gonna multiply by that by 2. Okay, and the starting point of the first sample will be anywhere in between 0 to 50% of the total duration. In our case, I'm going to just define as an A. So my first sample could be played anywhere beginning from here to here. Okay. Now, this is the part where it gets a little bit tricky, because now my second file should be playing in here. Then in order to calculate that, I need to subtract the sample starting position of the first one from my total duration. So that's my A minus B. So if my sample is starting at let's say 1 second after the total duration, then my second one should be at least getting 1 second before the end of the file. But that will just take us up to here. If I actually do just A minus B, then my sound file will be playing in here. Beginning will be here. And then you're not going to make a palindrome. What we need to do is actually subtract one more thing. We're going to subtract the duration of the sample itself, the current file duration. So in order to get the correct starting position of the palindromic side of the sample 1, I need to go total duration A minus the sample starting point of the first one, A minus B, and then subtract the duration of the current sample from there. Then we get up to this part. Okay, so here's the diagram of how I can do that. And although it looks a little difficult, it's basically the translation of this into the diagram. First, we need to detect the longest file duration. Okay, and we're gonna make a list of the file duration, and then we're gonna do that, and we're gonna make that go through the dot sort and dot last method, which will give me the duration of the longest file, and we're gonna multiply by 2 right here, times 2, and then we're gonna calculate the starting position of the first sample by multiplying that with the any number that's ranging from 0 to 0.5. That's my argument that we're going to control the argument lock. Okay, and my rate, the speed, will be controlled by the rate argument. Okay, now I also have this side. This is basically a way of choosing which buffer or which sample to play, which sample at which buff. And if my which buff is 0, it's going to play samp 1. If my which buff is 1, it's going to play I play samp 1. And then which buff, if it's my 2, then it's going to play I play samp 2. Okay, and my reversing position will be randomized in terms of order, and it could either start with the reversed position or the regular position, and I can control the amplitude. So that's up to B. Okay, now to calculate the starting position of the second half, we go through this thing. Okay, once again, it looks similar but more complicated, but all this complication part is basically doing this. Instead of a lock going into here to here, now, whoops, we do 1 minus whatever the location that we're gonna put for the B, and then you're gonna multiply that in here. Now, this part is here, right? We are going to, this part is here. Now, to subtract the current duration, what we are going to do is we are going to find the current audio file. Okay, and then first we need to kind of do a division, which you are not seeing in this text file, but we need to divide current file duration by the rate, so that if my rate changes, my duration also changes accordingly, right? Just like the way we change the duration of the envelope in our synthesizer, we're gonna do the similar thing in here, and then you subtract that from A minus B, the total duration minus the sample position. So it looks a little bit more difficult, but it's basically a graphical representation of what we did in here. Now, this is one of the cases where block diagram looks much more complicated than code, right? I can make this equation quite literally translate into here. Okay, so here I labeled the A, B, and C in my code. Okay, so total duration times 2, here's the longest times 2, A, and here's the position 0 to 50%, where I'm gonna do that, and my first sample position is here. First P equals position times total duration, and that's it. And second P is basically 1 minus 1 is the total duration minus the position times total duration minus the current file duration, which is calculated by buff-dur, which is this one, times rate in reciprocal, or divided by rate, same in our equation in here, in diagram. Okay, and this B and C is where we use the system clock, supercharger scheduler, to input the timing of the first P and the second P, the timing of the B and the C, and when the time comes, it's going to play the synthesizer accordingly. Okay, so for me, explaining this concept in code is actually more efficient than writing in diagram, but I think diagram also helps to understand how everything is connected. Okay, so that's what's going on in step 2. Okay, and when we run this code, now we have a little palindrome function where I can change the amplitude and which file to play and which location in terms of percent, so 10% in this case, and the speed, how fast or how slow the sound will be. So here, if I run this line, you're gonna hear a little bit of break, and then chicken sound, the buffer number 0 being played in palindrome. Okay. And here's the buffer number 1 being in palindrome, but in twice as fast speed at 20%, so you're gonna have a little bit more delay. But notice that there's a silence because our total duration is the twice as the longest file duration, which is much faster than the drum machine. So, and here's the buffer number 2. So what I want to do is I want to play all these 3, and it's going to create a palindrome of 3 tracks together. But but without the repetition, right? So essentially what we did was this thing. Okay, I'm gonna turn this off for now. Essentially what we did was basically palindrome with no repeats. So next step is to make a function that does the random repeats and random pitch change. That's your step 3. So we are going to make a little loop, and I can input how many times it's going to repeat, and it's going to make a repetition of, let's say if my repetition is 5, it's going to have either 5 to about 2.5, which will be rounded up to 3, I think. And I'm going to actually control how many times that palindrome will be repeated. And also I'm going to change the pitch range, the randomness of the pitch of the palindrome. And we're going to repeat that 3 times. One for the buffer number 0, one for the buffer number 1, and another for the buffer number 2. And we are just going to randomize the amplitude and the location of the files just for the sake of reducing the things that we can control. So we're going to repeat this for each buffer, and that's what you are going to get. So here you have a little APG that has 4 things to control: repetition of each audio file, and then how much of the pitch deviation you're going to create. And it goes from 0 to 1 or 0 to 100%. Okay, and that's what you're going to have in the code. So basically step 2 repeated with the certain algorithms in here. So here what you just, oh, oops, it's not saying, it's not making any sound. Oh, okay, it's making sound. Sorry. So in this one, you are sometimes going to hear some silence at the beginning because the timing is randomized, and sometimes we're gonna have like a 20% of the duration being silenced. But that ensures us to have a palindromic form. So when you are running a GUI, you can just wait. Sometimes when you press this, you're gonna have to wait a little to get the sound coming in. Okay, so what does the GUI do? It basically runs one line: APG.value and repetitions and the pitch range. Okay, it's going to have a little drag and drop box to drop your audio file, which is very convenient compared to the typing in the audio file path. But the essence is here, when you press the audio load audio files, it's going to basically load in the audio file and then run the APG function using the numbers that you choose in here: 0.5, 3, 4, and 5, which corresponds to repeat 1 to 3 and the pitch range. Okay, that's about it. GUI is a shortcut for the function, and instead of looking at the code, we just put the numbers using the number boxes, and we have a ways to conveniently import audio file. So let's do this, and let's add in the sound like that. Okay, and we're gonna use the default function in here and play. Okay, and for this one, it's going to automatically end too. And if you pressed record, and it's going to record the sound, and you can use that for your other projects. Okay, so let's just do this. I'm gonna just mute the sound, and it's gonna process it in the background. Okay, and we can take a look at that later. Okay, so that's about it, and that is how you create a APG app. Okay. Now, And the end page, I list some of the other projects that I have done in the CMPE, ISJS, RMHS, and SIOH. Oh, okay, we made a program. We made an audio file right here. And you can verify that it's a sound palindrome by looking at the waveform. Right? Okay, in the middle, they look like a mirror image, which means it's going to be a palindrome when you play back. Okay, but let's go back to our slideshow. Okay, so here is the other CMP project that you can check out. But also, I start to list some of the inspirations for the project. This concept of audio palindrome and making those audio palindrome is something that I was able to do during O4 Sound Art Workshop in 2006. At that time, I was able to do it, but it was all manual. I used the DAW to make a palindrome by calculating the beginning and the ending position and carefully putting them together for a few days and a little bit more days to to exactly calculate the position of the audio palindrome. But in 2020, I'm able to do this in algorithmically and spend less than few seconds to create an audio palindrome. But the beginning was from here, from All for Sound Art Workshop, and these three teachers who are amazing composers guided me through it, and I owe a lot of this idea being into realization to Yves Daou, Oake Parmenrud, and John Oswald. Here's the link to their music and work, and I strongly encourage you to check them out too. Okay, that was APG, and I'm going to, I hope I can see you in the next CMPE episode. Thank you.